Video 1 of Chapter 6, we are going to be exploring discrete random variables. And so starting off with our introduction to discrete random variables, what is a discrete random variable? So a discrete random variable, by definition, is a variable that has a countable, or what we would call finite, number of outcomes. So, for instance, number of siblings is countable, unless you're Nick Cannon. Oh, burn Nick Cannon, sorry. Or number of states visited. There's a limited number of states visited. And shoe sizes, there's technically a countable number, and shoe size is a discrete random variable where it's not all whole numbers, right? We can have half shoe sizes. And so it doesn't have to be a countable in terms of whole numbers. It could include decimals and fractions as long as it is countable, and there are a finite. It's not infinite in nature. Now, the opposite of our discrete random variable was something that we've talked previously about in Chapter 2 with a continuous random variable. And so a continuous random variable had an uncountable or an infinite number of outcomes. Now, we specifically talked about normal distributions back in Chapter 2, and we talked about uniform distributions. But back in Chapter 1, we also talked about skewed left and skewed right and bimodal. And so a lot of those are considered various types of continuous random variables. Heights of people, we can have decimals and fractions that aren't necessarily exact, decimals and fractions. We can go in between. Someone could be, just a hair, literally a hair taller than another person. And in the end, we have this infinite number of heights that people technically could be. Now, where this is leading to is a common question people will ask me is, what are the odds that you have 3 girls? I have 3 daughters. And so we looked at this question back in Chapter 5, and we used a simulation to simulate what would be the probability of getting 3 girls out of 3 children. And this also ended up being the same thing as 3 boys out of 3 children as well, assuming a 50-50 probability of having a girl and having a boy. So what we need to do first is, if we want to consider this to be a discrete random variable, because out of 3 children, I can only have a countable number of children out of 3. So if I were to define my random variable, I would let x equal the number of girls out of 3 children. And so it's important, especially on the AP exam, that you define your random variables. You shouldn't just blindly use x and just say, I'm just going to let x be this. And I'm just going to do the problem with just x and x, 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 x. And you might be going, what does x represent to this problem? Because you might be accidentally misinterpreting what x really should be. So on the AP exam, you should absolutely define any random variables that they give to you that aren't already defined. Now, we're going to organize a discrete random variable with a table. And this should look kind of familiar from last chapter when we dealt with probability distribution tables. Now, the one difference between this chapter and last chapter's probability distribution table is that our first row, typically our first row, it doesn't have to be the top one or the first one, is that we must deal with quantitative values, meaning numerical values. So back in Chapter 5, our first row just really represented the events that could happen, and they could have been categorical. So some examples that we did, we could have had heads and tails for a coin flip, but that wouldn't work as a discrete random variable because heads and tails are not quantitative. We did an example of rolling a die, and that is quantitative, of rolling a 1, 2, 3, 4, 5, or 6. So rolling a die is a quantitative variable, so this is a discrete random variable. The suit of a playing card, not quantitative. Rolling 2 dice and adding up the sum, that is quantitative. So we could do a discrete random variable related to the sum of 2 dice. Now, let's get into filling in this probability distribution table for my example of having 3 girls out of 3 children. So, theoretically, out of 3 kids, I didn't have to have any girls. I could have had 1 daughter. I could have had 2 daughters, but I ended up having 3 daughters. Now, in terms of the probabilities, this is something that we talked about last chapter. So I'm just going to fill these in And we're not really going to focus on how did I get these probabilities. So I have a 1 in 8 chance of having no girls, aka 3 boys. I have a 3 in 8 chance of having just 1 daughter out of 3 children. I also have a 3 in 8 chance of having 2 daughters. And last but not least, the probability of me having 3 girls is 1 out of 8, which is 12.5%. So there is the table filled out with our quantitative values in for our discrete random variable and all of our probabilities. Now, just to jog your memory, our basic probability rules will still apply here. So all of our probability values have to be between 0 and 1, and they could be 0 or they could be 1. And the sum of all of our probabilities have to add up to be 1. So 1/8 plus 3/8 plus 3/8 plus 1/8 is 8/8, which is 1. Now, if we were going to talk about to describe the distribution of my discrete random variable, if I looked at a graph of a histogram here, we could see that this graph, if it went to 1/8 and then 3/8, 3/8, and then back down to 1/8, that it's symmetric. It's perfectly symmetric. But we could also say that it is, roughly approximately normal here. I mean, it's not the perfect bell-shaped curve, but it roughly fits to a bell-shaped curve. And are there any outliers present? I wouldn't say that there are any apparent outliers. We're not going to use the 1.5 IQR rule to determine this, but I would say it doesn't look like there are any outliers. Now, in terms of center and spread, for right now, we're just going to kind of discuss, what do you think the center would be? And so the center, would really be right in the middle, right? If it's perfectly symmetric. But is that 1? Is that 2? Is that 1.5 girls? Can I have 1.5 girls on average? That seems kind of weird, right? And then what would the spread be? If I use the mean as this, is it like 1? Is it slightly less than 1 for a standard deviation's worth? I don't know. So we're going to use a different example here that's not as obvious, at least with the center. We know in this one, the center is going to be right here to split it perfectly down the middle. But again, is that 1? Is that 2? Is that 1.5? Can we have a decimal for a center for number of girls? That doesn't seem right. So on the AP Stats exam, there's a formula sheet that you will get to use, and I will let you use this on my chapter tests. So there is a formula for the mean of a discrete random variable. And so you'll see mu sub x, where x is our discrete random variable. And another way of seeing this will be a capital E with x in parentheses. So it kind of looks like probability of x, but it's E of x. And the E stands for expected value. So the mean and the expected value are one and the same. So those two terms can be used interchangeably. Now, what the formula is telling us to do here is that it's telling us to take each of our different values for our discrete random variable. So the sub I here means individual the individual events of x. So take each of those events x and multiply them by the respective probabilities. And once you have multiplied every value by its probability, then you're going to add up all of those values. Now, the nice thing is we're going to let our calculator do all the dirty work for us. But we're going to need to show, especially on the AP exam, that we truly understand how this formula works. And so we're going to do abbreviated work instead of writing out all of the work. So it'll make it a little nicer. Likewise, the standard deviation formula is on the AP Stats exam formula sheet. So this is like using the standard deviation that we used back in Chapter 1. It's the average difference between each value and the mean. So the average is a really weird way of saying average because we're not just adding up all the values and dividing by how many values we have. If we were to take the difference of the mean and our individual values here, then in the end, if we were to add those up, we would always get 0. And so we said to get rid of that 0 sum, we would square all of these differences so that all of our differences would become positive instead of having a mixture of positives and negatives. And then we're going to multiply that by our probability for each of our events. We add up all of those squared times probability differences, And then to undo the squaring process, we're going to square root the whole thing. And again, you don't really have to worry about this formula in general because we're going to let the calculator do the dirty work for us. We just kind of have to pretend like we're going to use this formula. So again, we're going to show abbreviated work, and then the calculator will come into play. All right, let's go through a full example now. So high school students in Michigan sometimes get these things called snow days, like old people used to get them. You know, back in the 1900s, there used to be snow days. We didn't have e-learning days back then. In the winter, when roads are so bad that school is canceled for the day, define the random variable s to equal the number of snow days at a certain high school in Michigan for a randomly selected school year. The table gives the probability distribution of s. So if I wanted to describe the distribution of s, well, okay, let's start with shape and outliers. Shape, I don't have a visual to look at, but if you consider, since these are all already in order, from least to greatest, from 0 to 10, if I were to graph this as a histogram, notice that the probabilities start off higher, and then they get lower and 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 lower. So just imagine this thing starts off really high, and it starts getting closer and closer and closer and closer to 0 until it gets to that 1% down there. So in the end, this would end up being a skewed right distribution because the tail is tapering down towards the right end. Now, outliers, we are not going to mathematically determine if there are any outliers, but do you believe there might be any outliers in this data set? And you might go, I don't know, maybe 9 and 10 because they're only 1%, maybe 8 because it's 2%. So I'm just going to throw out there, I don't know, maybe 9 or 10 might be outliers. I don't know. But now we're really going to focus on how do we get that center and spread? How do we get that mean and that standard deviation value? So this is where I'm initially going to write out the work for this. I'm going to call what I call abbreviated work because I'm not going to write out everything that's going to make up the entire mean. And then I'm going to show you how do you get the mean from your calculator because that's going to be the easiest way to get it because we can do the mean and the standard deviation with one set of commands in our calculator. So for the mean, also called the expected value. That's why on the formula sheet, you'll see this capital E of x. X in this case is just the random variable. So for our example, x is s, the number of snow days, right? So we could say this is the mean of the number of snow days, or it's the expected number of snow days, and it's equal to the sum of each individual value that we could have as a snow day, 0 through 10, times its respective probability. So what we do is we go through and we start with, let's say, our smallest value of x, or in this case s, which would be 0 snow days, and we multiply it by its probability of 33%. And then we add to that, that's what the summation symbol here is for, and we add to that then 1 times 0.19, and then 2 times 0.14, and we keep going and going and going. And this is what I mean by abbreviated work. We're going to use this ... notation to really represent skipping over the 1 through 9. So I'm going to show the work at the very, very beginning for the 0 case. I'm going to show the work at the very, very end for the 10 case. But in between, we are just going to do this ... notation. So here is what I would again call the abbreviated work for the mean. Now, what does all of that come out to be? Just hold on. We'll save that. I'll show you how to do it in the calculator. How do we write out the work for the standard deviation? Well, here's one thing we'll have to come back and fill in because one part of the standard deviation formula is we need to know what the mean is. And I just said, we'll come back later and we'll figure out what the mean is. So we can at least initially write out the abbreviated work for the standard deviation. And then again, we'll come back in later once we know what the mean is, we'll fill that in. So we need big square root. And then again, we're going to add a bunch of stuff together here. What are we going to add? So parenthesis. And again, we're going to do this for the very beginning case. We're going to do this for the very end case. And we are going to ... our way through most of this probability distribution table. So it says x sub I. Again, that represented the individual values here. So we'll start with the 0 minus, and then I'm going to leave a little blank here because I need to go fill in what the mean is. And I don't know what it is yet. So we'll just hold on to it. So just leave a little blank there. And then we need to square that difference. And then we're going to multiply it by its probability. It's 0's probability. So times 0.33. So that takes care of the first one. Plus, dot, 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 plus. Now let's go do the same thing for the 10 case. So the last individual value is 10 minus, I don't know what the mean is still. So again, put a little blank there, square that, times its probability, 0.01. Now again, we'll come back later and we'll figure out what does all of this come out to be. Because again, we got to come back and fill in what that mean is. So how do I do this in my calculator so that I can come back and say, oh, look, yeah, I totally typed all of this into my calculator. Not really. So in our calculator, you need to go to Stat and then Edit so that we can put some data into our lists. So if you have data in your list, you can clear them out. But I'm going to use list 1 and list 2. If you need to use list 3 or 4 or 5, whatever list you need is fine. So in list 1, I put in all my different values that represent my snow days. And in list 2, I'm going to do the corresponding or matching probabilities for each of those number of snow days. So notice my 0 is right next to my 33% probability, all the way down to my 10 is right next to my 1% probability. So once you put in all of that data, and if you need to pause the video so that you can do this on your calculator and make sure that it matches exactly what I get, you can pause the video and do that. But once you have your list 1 and list 2 in, then we're going to go back and press the Stat button. You're going to press the right arrow key so that you go over to the Calc screen. And then we're going to select option number 1 for one variable stats. So this isn't the first time we've dealt with one variable stats. We did it a lot back in chapter 1 when we wanted to know about, all the different measures of center and the measures of spread and the 5-number summary. We've definitely used this quite a bit, but it's been a little while since chapter 1. So again, select one variable stats, and depending on how new or old your calculator is, if you have a newer calculator, it gives you this nice table. And for list, we want to put the actual values for our snow days. So for me, that was list 1. Frequency list. This is the very first time now that we get to put something into the frequency list. The frequency list is going to be the list with our probabilities. So for me, that was list 2. And then I'm going to hit calculate. Now, if you have an older calculator that doesn't have this nice table option here for you, on your screen, once you select one variable stats, your screen says one variable stats, and then it's got a blinking cursor. And what you are going to need to do is put in L1 and then do this comma and then list 2. The shortcut for doing list 1 was to press the second button and then press the 1. So if you press second 1, that should be the shortcut for list 1. Then you have to find the comma button. The comma button, if I remember correctly, it's either above the 7 or it's above the 9. It's one above those two things. And then for list 2, remember the shortcut for list 2 is to press the second button and then hit 2 for the shortcut. So you should have one variable stats, list 1, comma, list 2. That second list always has to be the list where your probabilities are in. So once you click enter from there, whether you have the new or the old calculator, then we get all of our results. And the X bar represents the mean that we're looking for. So the mean is 2.17. And then when we go down, typically we use that SX for the standard deviation. But you're going to notice it is completely blank. There is not a number there. So therefore, we are going to use the sigma x, the lowercase sigma x here. So this is going to be our standard deviation. So this is the one and only time that typically we use the sigma x to represent the standard deviation. So now what I'm going to do is I'm going to go back. I'm going to go back to here where we were working on our mean. And we're going to say, hey, all of this, I totally threw all that in my calculator. I typed in everything in there, and that came out to be 2.17. There's the mean. Now, what about standard deviation? Remember, we needed to go plug in the mean. So we're going to go plug in 2.17 into those two places there. And then we're going to act like, hey, I totally typed all of this crazy square root mumbo jumbo in my calculator. And it came out to be, I can't remember what the number is now, 2.41 if I go to two decimal places. 2.41. 2.41 is the standard deviation of the number of snow days. All right, so we've got our mean, we've got our standard deviation. And again, the easiest thing in the world to do to get both of those, the mean and the standard deviation, is just to use your calculator's list to put in your normal numbers, your actual values, and then the corresponding probabilities. Use that one variable stats feature. And again, this is the one and only time that we're going to use that frequency list to put those probabilities in. All right, so now let's jump to here. So now here's everything. We had a skewed right distribution. Outliers, maybe 9, maybe 10, we don't know. The mean was 2.17, and the standard deviation was approximately 2.41. All right, so the mean of 2.17. What exactly does that mean? Don't be like Michael Scott. Have no idea what to do with that number. Because on the AP exam, they will often ask not only to calculate the mean, but also interpret the mean in context to the situation. So let's talk about what does it mean that the mean number of snow days is 2.17. So specifically, if we were to record the number of snow days, not for just 1 year, but for many, many school years, because the one thing that maybe you didn't catch, let me go back at the beginning of the problem, right here, was it said the number of snow days for a randomly selected school year, okay? So the mean isn't just about what happens during 1 year, but the mean represents what happens over the course of many, many years. So if we recorded the number of snow days over many, many years, some years there may be 2 snow days, some years there may be 8 snow days, some years there may be only 1 snow day, but you're going to have all of these different numbers, right? If you were to calculate the mean or the average of all of those many, many numbers that you collect snow days from, then we would expect on average for there to be about 2.17 snow days for each of those years. Okay, so again, on average, about 2-ish snow days. Some years may be more, some years may be less, but on average, in the middle, it should be around 2.17. But now, 2.17 snow days? Can you have 2.17 snow days? Does the 0.17 mean you get like an hour early dismissal? Like, hey, there's a snowstorm coming in, we're going to let you guys leave an hour early. Maybe, but not necessarily. So just keep in mind that the mean is more of a theoretical value, and it doesn't really represent what's actually going to happen there. But the mean could be an actual data value from the data set. So let's say I did all that work and I calculated that the mean was exactly 2. Well, 2 really could happen, right? You could have 2 legit snow days. But oftentimes the number that we're going to get is going to be a decimal or a fractional value. And it may not actually be able to happen, but it just represents what that theoretical mean is. Okay, it's not just what happens in one trial, or in this case, 1 school year, but over many school years. Now, standard deviation. How do we interpret what 2.41 really means? Now this, I have 2 different ways you can do it. All right. The first one really reflects the way that I showed you earlier in the video of how we would interpret the standard deviation, that it's the average difference between each individual value and the mean. So one way to interpret it is there is about a 2.41 day average difference between the number of snow days and the mean. And remember, the mean, if you want to throw in the number, you could say, and the mean of 2.17. Now, a different way that you could interpret standard deviation is to say that your number of snow days typically varies. So instead of saying average difference, we could use the phrase typically varies from the mean by about 2.41 days. So either one of these is acceptable. I've pretty much always kind of focused on this first one, And then it wasn't until recently I learned about this other way that you could interpret standard deviation. So whichever of these two ways you prefer, and I want to bet most of you are probably going to like this second one because it looks shorter, right? So the number of snow days, what we're measuring, typically varies from the mean by about whatever that standard deviation is. So either one of those two works out. All right, the you do problem. Did you know that there are 5 Home Alone videos? There might actually be 6 at this point. I don't even remember. So believe it or not, there are some weirdos out there that have never seen a Home Alone movie. And I find that shocking. But every year I'll talk to students and they'll be like, oh yeah, I've never seen a Home Alone movie. And I'm like, what planet are you from? So this was data collected from a very large sample of high school students. So some students haven't seen any of them. Some students have seen one of the Home Alone movies. Some of them 2s. Some of them 3. I don't know. What's that question mark? I don't know. Some people have seen 4, and some, not very many of them, have actually seen all the Home Alone videos. So what I want you to do is to go through and answer these 5 questions based on this probability distribution of the number of Home Alone movies watched. So do those. We'll discuss those next day in class, and good luck.